So hello everyone. So today it's Bernard that's going to discuss about debugging and profiling scientific code.
Good morning, everybody. This morning I'm going to talk about the debugger. There are many kinds of debugger installed on the CC cluster, which are the GNU debugger, and it's nearly the same. In fact, it's the Intel debugger. It's the GNU debugger with some enhancements done by Intel to take the last point of resource of its processor. I'm logged on Lemaitre 3. These exercises can be done on, there are some exercises, and they can be done on Lemaitre 3. And I'm used, in fact, the Intel Cluster Studio, which is a full package of plenty of software, which provide some profiler, advisor, inspector, amplifier, and different stuff like this. This different software, piece of software, I will present that to you this afternoon. So for the current session, I'm only focused on GDB, the debugger. Of course, you know, also, if you want to follow the slides, you can open a web browser and take these pages. This is CISM UCLouvain/services with a S, with a capital S, formations with a big F, a capital F, and then Intel Cluster Studio. And then you get the Intel Cluster Studio, but here I'm focused on GDB, which is Intel with extensions. On Lemaitre 3, if you want to have all this piece of software and of course also the compiler and library from the version of Cluster Studio installed on Lemaitre 3, you have to source some file. But I've done a small script to do that more easily for you here. And if you want to copy everything, to have all the materials, you can make a CP or CP come after. You can source it. Source TMP Intel Cluster Studio. TMP is a temporary subdirectory. Everybody can read it. Everybody can copy things from this according to the permission I give to this subdirectory ECS. But it's open for everyone. ECS sources. And then everything is logged. The Parallel Studio environment, the advisor, the inspector, the VTune, and those software I will present this afternoon. But for the debugger, we need, of course, the Intel Parallel Studio. You see what it contains. It sources every script, small script, and the software is saved in a long place there with the binary at the end. And it's not a module. We can. There are some module, for instance, I think amplifier. The module is defined, but I will do that if you prefer to play with module. But it's a little bit hide this software, and this is why they don't have module defined. But I will do that. I can write it. Let's see the contents, for instance, of this small sources cat. The copyright of Intel, the directory and the product where it's installed, and then you search for the architecture and the platform and so on. It exists for a 32-bit architecture or a 64-bit Intel architecture. This piece of software also exists for a Mac, for Linux, of course, for Windows also, and it sources everything it needs. So if I, for instance, check for iFortran, I have the version installed there, which iFortran, which ICC there, and which, of course, GDB. This is the GNU debugger. You see, it's not into Intel software, but you know this trick with Bash. When you use the tabulation button, it complete everything which begin with a GDB something tab 1 time, 2 times, and you see it exists. GDB add index, GDB high, GDB GDF, and GDB US. I will explain, but this one is the GDB from Intel. So it's the GNU debugger with Intel enhancement, which you see. So this is what I present to you. The sources of the variable. Intel provide a lot of very good documentation. So, for instance, this slide is a web page. So if I middle click this, I open a new tab. And so the new tab will be open there. And then I can come back to the formation training, my own slide there. It's where I will work. So sometimes you will be confused. Where is that found on the slides? So check where is the tab. So middle click there, I open a new one, and this is all the documentation and how to search. For instance, you want to search, you see about headvisor, compiler, plenty of things, debugger, the programming language, and then you will get plenty of tutorial or webinar of direct documentation, PDF. It's very complete, and you can browse and search. This is very interesting. So, of course, when I search for when I source this script, I get the iFort. I show you the version 18 with Fortran 19, Fortran 77, C++. Also, the matkernel library. I'm going to talk again about matkernel library because there are plenty of tricks to take the full resources of this important piece of software for the Intel compiler world. And the GDB. After that, there are also trading block. So that this afternoon, now I'm focused on GDB. GDB is a tool. What's you have a program, and this program doesn't behave well, fail during the execution. It failed with not very understandable message, segmentation violation of bus error or whatever, and you are a little bit annoyed. How to find the solution? How to understand the reason of the crash of this program? And of course, you see that this is systematic. If you run that on this machine with this compiler, you get the error, and sometimes it happens. It's a bit it's the difficulty of the thing. With another compiler, it doesn't happen like this. And even more vicious, it depends on the level of optimization. So if you take a too high level of optimization, minus 0.3, 0.2, even if it's the default, sometimes produce an error during the execution of the code. So a good way to do and to find a solution is first to compile without any optimization with the minus 0.0. And you see, yeah, of course, it's slower because there are no optimization in the loop, optimization of inlining, subroutine, of aligning data or of whatever, or changing the index in case of double imbrication of do loop. It depends. You know that in Fortran it's column first, and in C it's line first. And so depending on the language, if you make the G or the E in the double loop out in the outer scope, the performance will be efficient for one language and disastrous for the other one, because you know the use of a cache system, and the system of a cache on the CPU. We cannot we may suppose that when we use some data in an array, we will use the next one at the next step of the loop, and so we put the full loop, the full column in C language case inside the cache, and so it will be efficient at every step of the loop. There are no what we call a cache miss. The data is already available in the cache. But if it's not well aligned, or instead of taking the line, it takes the column, at every step of the loop, it will see that, oh, the next data is not there. I have to take that from the RAM, from the slower portion of memory. And to make that, I have to flush the cache, the local fast memory area, and make a switch back of the other portion containing the needed data and the neighbors, and use it. And the next step, if it's missing again, it will generate plenty of cache miss. So in this case, the code will be very slow. This is why we use improvement, and the compiler are clever enough, GCC or Fortran compiler or Fortran group compiler are clever enough to understand that we have to align the loop and the array in such a way that there will be less cache miss. So GDB, your code crash. It's a Fortran code, a C++ code, or even a machine code. You can check, but it's a little bit rough and hard. You can see and check where it crashed. Parallel code can also be debugged. This is sometimes not so user-friendly, because you have different windows opened on your screen. Sometimes you need big screen. You can select the threads, so the portion of parallel code you want to investigate, and you may suppose that the other threads do the same behavior, but you don't look inside them during the debugging process. Otherwise, you have to look a lot of windows at the same times. You can also, with a debugger, debug a parallel program. Or another way to do that, and this is a GDB extension, is to serialize a parallel code. So instead of running that into parallel, the debugger decided, okay, we do that sequentially, and it's more easy to debug. I said that sometimes the level of optimization influence the behavior of your code. It's because we take more aggressive and more rounded algorithm to search for the square root, to search for the sinus or the tangent or something like this. And if this too much aggressive and too much rounded or imprecise code generate imprecision in the real number, it can generate instability in your models and provided you wrong result, or even worse, impossible result, and it crash your program. So the level of optimization and the selection and of the mathematical routine you use can influence the result of the debugger. How to imagine you don't have any debugger. What users sometimes do, it's a little bit hard, but it's feasible. He makes some write command to search where it crashed, because you see it starts and it seems to run, and then it crashed, but you don't see where. And so you suspect this subroutine to be the cause of the problem, and you put a write hello, I'm in this subroutine, or hello, the value is a something like this. Okay, you can do that, but quickly it will be a little bit rough, and it's slow, because yeah, the portion of the code you have to compile it and to examine it and to change. But sometimes it's a way to do that. Also, you can use strace. Is the way to follow the execution of a program. I can show you this is not difficult. For instance, strace ls is show you everything it does with, just like if it's debug, not really, but some interesting information is it gives you every library it opens to start the executable, and the way you search the library, and then the file it opens, it read, and you will see where it crashes if it's your own program sometimes. And it's a trick. It's a first and a very fast way to search a problem. So strace. Trace a system call and sign-out. And of course, there are plenty of arguments, but one interesting is to follow, I think, to follow the child, and because when we start an executable, it starts another one or another portion of, and you can follow, not to have the first executable to be traced, but also the fun and so on. Yeah. Let's get started with the debug. I open it. There. Open a new one. This one I can close. Getting started. It says that prerequisite doesn't matter for it's installed. Well, it's installed, it's not a problem. What's a Xeon-Phi? Intel talked a lot about Xeon-Phi coprocessor. It's its own a little bit old solution for the GPU. It's nearly 10 years ago. He decided to implement and to design an accelerating card, a PCI card that you put inside a server, and those cards have plenty of small CPU, just like a GPU for NVIDIA or other GPU company, and those processor can take a portion of the code to execute it in parallel inside this card and give back the result. So it's an accelerator card. We used to get one 3 years ago. It was some exploration, and the use of man-back is to provide exotic also CPU, exotic architecture, to see if in the future the user will follow this way and will investigate a lot of effort, lot of development inside this kind of architecture. It was not the case, so we remove it. It's in the box. Those CISM, that was Night Lord, the code name of this kind of CPU. This card have 60 core inside a small PCI card. It seems to be small in comparison of GPU of today. But the main advantage, and this is why Intel was pretty sure, yeah, we're gonna win the market, is this CPU was x68 architecture. So it was in fact old Pentium processor put together inside a PCI card. And those processor can be seen in two ways. It can be seen just like an accelerating card, and with a specific library, for instance, Matcan library, who put the work directly, just like GPU, put the work inside this card and get the result. Or it can be used just like plenty of operating system installed on every processor. So it's a small cluster inside a machine. So this machine you can install, or this machine can even be a node of a slum of a bigger cluster. But inside this node, we have a small cluster, and we can submit job, and the job will be just like an ordinary MPI job, and start and run on the small nodes, which were not very fast. It was 1 gigahertz Xeon processor. So the people were a little bit disappointed. Yeah, it's easy to use because it's the same architecture. Just some trick to take into account that the fact that there are not so many memory, but the code is the same on the host node and the processor, the accelerator card. It's a great advantage because we have a specific training session with CUDA, and the language is very specific. The effort to port code on CUDA environment seems to be more important. Yeah, of course, nowadays we have SDK of software development tools to help and to assist the developers. So it's more easy today to develop with CUDA or with NVIDIA card with V100 we have some, and in the next training session there will be specific training session with CUDA. So still 3 years ago, now it's discontinued. Intel must admit that he have lost this war, and nowadays the most powerful cluster in the world have plenty of GPU from NVIDIA, and it's a way, an easy way for him to be on the board, on the list, because it provides plenty of floating point of operation, and you reach a very large amount of gigahertz. But truth is, nobody check during the life of a cluster if all the CPU are really used. For high development, there are tools, Tensor, and so on. There are plenty of investigation to use this GPU, but in the traditional and old-fashioned way, HPC world, it's still a little bit a challenge to use this GPU, still nowadays. So I just explained what was CISM for the small story. So this GPU, of course, this debugger, sorry, can work with CISM and debug on the accelerator card the code, and we can choose which one on which node we want to debug this code, and it's a way to do that with a client and server with a debug agent working on the accelerator card. We will not investigate that, but it's easy. It's a way to do that. It explains everything, how to install. GDB can be bundled and integrated into Eclipse. I don't know if there are people, it's more in the world with Visual C++ or something like this. Intel products are integrated into this. So if you want to develop on Windows, the advantage is it's the same compiler at the end. You can compile it on Linux, but nowadays I will not focus on Eclipse, but more on the traditional command line GDB -IA. This manual is well done. It's a PDF with more than 300 pages, but there are a lot of blah blah and things which are very fastly read. So, you see that inside this GDB manual, you have the sample all the commands. But the easiest way to do that is to play with the GDB. We will do that at the end of this session. Play with GDB, or even more user-friendly with DDD, which is a graphical environment around GDB. So you have not to remember how to set a stop, a breakpoint, or things like this. It's more easy with DDD. But things are interesting with this PDF manual is the explanation of what are the enhancements done by Intel, which are not available on the GNU GDB, the command and ordinary GNU GDB. So they have added some enhancement, for instance, how to to debug a data race condition is when you run a multi-threads execution. If every threads or a portion of threads running in parallel try to access the same amount, the same portion of data, but without any synchronization, any discussion between them. The first one decided, I write and I modify the result of this portion of data, and the other one take that just like the input or the data needed to make the calculation. And if it's already modified by another threads without any synchronization, there is some what we call the data race, and the data are irrelevant, and it's very difficult to analyze that if it's not well designed, if there are not good synchronization point on multi-threads code. sorry. It can be a challenge to think to see what's happening inside the code you have to debug. So the Intel parallel debugger extension provide a way to do that, and you set some commands and you decide to enable that, and during that you can even enable that for specific variable, so for specific array or thing like this, by using some filters. So you decided to put filters for some lines, some expression, and some value of variable. You see, and after that you can press the filter you have set. So this is the way Intel help you to search for data race inside multi-threads code. Data race. Where am I? I'm sorry. Data race, and also speculative execution is, we suspect that, how to explain this, it's also an extension provided by Intel to take the advantage of a register, and in case of one execution can have a different input of value, and according to a condition, it will branch on this value or this one or another one, and it's what we call speculative execution. It puts different branch of condition inside the pipe, and it branch according to the value of the condition, the good one, and so it increase the speed, the overall speed of a code inside an Intel processor, and it's a way to debug this speculative execution. Hasbound help you to debug Intel code if, for instance, you access a pointer outside the definition and the size of the array. You are outside the scope of the portion of memory of the array, and so there is what we call a bound violation inside this array, and with this debugger, by using the command hasbound, and you specify the array or the pointer to this array, you can examine, and you are advertised and you are warned when you are out of the scope of this array, and you get the prompt at the line where it happens. So it's a convenient way to find that. All those improvements are also used in the other piece of software I will present this afternoon. So this improvement, including to GDB, are also used for the profiler, for the inspector, or the different tool provided by the Intel Cluster Studio. And this is what I said previously about the serialization of parallel application. Due to the fact that it's very difficult to debug a parallel code, it's feasible, but it's difficult. A convenient way is to serialize with the Kilk-Intel. You serialize the execution of a parallel application, of course, with correct result. So in the debug process, it's more easy because you follow the line of the step of the execution instruction after the other, not in parallel. And you decided to activate the serialization with the Kilk serialization on. The 5 things improvement provided by Intel on the GNU debugger is how to debug OpenMPI and multi-threads OpenMPI code by displaying what they call an OpenMP team, which is a set of threads which are executed in parallel due to OpenMPI directives, saying, for instance, this loop, you recommend in the code, do that loop in parallel, and it becomes a multi-thread loop. Every threads take a portion of the count of the loop in parallel, and so it's faster. And so it's a OpenMP team. And there is an OpenMPI training session, so I will not focus and insist on the OpenMP before you get this training session about OpenMP. So this is the GDB manual. It shows you plenty of interesting information of how to run it, how to control GDB, how to. But of course, you still have the GDB, sorry, minus IA, minus help. And you see, when you start a GDB, you specify an executable, your executable, or you can add, if you want more, to be more specific, also a codon generated by the execution of the code. And you can attach the GDB to a running process by specifying its PID, process identifier, or like this. You can specify the directory where the sources of this code are located, and plenty of other stuff. for more information, you can also take help in the info of GDB. Okay, thank you. So this is what I said when we the Intel extension, but one comment and general use, it's the same on the GCC or Intel CC. In order to put debug information, you need to add -G. -G flag is the way to integrate the source code inside the executable. So when you debug it, you will see the contents of your code. If you forget -G, you will only be able to debug a machine code program. It's not so convenient, of course. And the extension of Intel is what I said: debug parallel, checkpointers, or inside the debugger, set the serialization on. And also you can debug OpenMPI program. I can suggest you to copy like this CP. I've put that into TMP, a DDD subdirectory, but copy that in recursive way. You can preserve the date, it's not important. And you put that inside your home, for instance, like this. I will not do that because it's already done. And then you can go inside DDD and see that you have some C++ program or C program there. It's some example. Oh, this is previous execution of this. We can then play that. Crash CC. It's a program which have a division by 0, in fact, and it generate, of course, a cordon. To compile it, sorry, -G, minus no optimization, for instance, O0, crash. By default, it generates a out program, the default name, or if I want to put the name, explicit name, for instance, -output, crash with the G and O0. If I execute it, I have a floating point exception. I see nothing else because, and sometimes we forget that, we want to generate the cordon. What's a core? A core is the full state of the program at the moment it fails. So it's the portion of the code of the program and all the value of the variable and the environment which were on the stack at this moment, on your own stack at the moment the program crash. So if I set by ulimit -C to 0, but I set that to unlimited, when I execute my program, I've generated a cordon which is bigger, of course, than the size of the program itself, because it contains everything into a big package with the value and the current loaded library and so on. Just like, if you want, a static code plus the value of the variable at the moment it fails. And that you can try to debug. You can try to debug with GDB, or even, if you prefer, with DDD. DDD is a graphical data display debugger. it's the graphical environment wrapped around GDB with plenty of tips and so on. And it uses, in fact, GDB. So you can open a program or a coordinate or a source. You will find the sources normally because it was compiled with -G, open program, and if I select this one, you see it discovers the sources and you make run. You can type in your GDB prompt or using the button there, which will be the same that then using this. Maybe it's small for the size. It's not. I don't have to choose to increase the size of the text. Don't know.
I don't know. There is a question, Bernard, on the chat.
Mm-hmm.
Do you want me to read it or you want to read it yourself?
Is it possible to thread an example, a bug in a simple program code and a method of debugging in cluster? But the program, the example is very basic, but it's an example. It's a small C++ program and with a division there of a value. And if I run it, it says that, oh, I'm crashed there, the return of this. And I can print value there, print A. A is the value of 3 at the moment. And print B. This is normally print. I don't know if it works, this. Division by 0. This is the reason of the segment, the floating point exception, arithmetic exception in this example. You see, I can decide to put a break there. Nonsense. Break there. If I run it, where that use run, it reached the breakpoint and then it stopped. This is the advantage. You have a bit code, you put a break at the beginning, and then you can go step by step. Where is the button to go step by step? You see that I'm more used by next. This is the call of the subroutine, div integer, then it goes to the subroutine with A and B and put and return the division. And this is where you get the segmentation violation because of the value of the argument there. With A and B. So you see, by putting a breakpoint at one point and advance instruction by instruction, you can progress slowly in your code and print all the time value of variable, or even set value. If you want to decide that B is 2, so B, I remember, like this. Hold on. Sorry. To crash CC, the division by 0, floating point. You can get with GDB the list and the content and print the value of X. Okay. Crash 2, second program. We can try to compile it and to execute it. Where is that? Backgrounds. the core, if I want to open a core, it will be the same, but I will generate a core with the second program, crash 2. -G, crash, CC, -O, and put that into a name, crash 2 dot or -G -O0 to remember the same syntax, same convention I choose. What's inside crash C? A small C++ program. B, count B, return 0, and void if I run it. This time, again, it prints the first value with the cout there, A, but for this one, it's not, the syntax is not correct. It crashes, and you see the codem is there. Can try to debug it with GDD again. Where is my GDD? There. File, open the core, and I choose what's the number? This one, the last one. Open, and open program. Crash. No, this one. Where is that? Why doesn't suggest this one? Yeah, find it. He said that the core file may not match specified executable file. Okay, this is why I have to open the proper crash 2 program. And the core was generated by this executable, and with the segmentation fault, signal 11 there. It reads the contents of the executable, compiled with -G, so you can find the sources. And then I can work with my GDB. You can run and then check where it crashed. This is the full explanation of the first one, the second one. This one, crash 2. You compile it with -G, and you generate a core. You debug it, you run it, and you say that there is a segmentation violation. Where? And this time, this program does not crash into the portion of the code developed by the user, but inside a mathematical C library there, the default. So it's very difficult to search for the variable, and you try by putting a breakpoint, -B, at the main program. And so when you run, it reached the breakpoint and it stopped. And you go the next step, and step by step, you reach a value where you get this crash, explaining that the value of IP variable is something completely irrelevant, and you can, when you print the value of the pointer and the contents of the variable pointed by IP, you see that this is in fact the problem there, because the pointer was not initialized, and so it points to somewhere in memory, and so the value of this this variable pointed by an uninitialized pointer is something not relevant for the execution of the code. It points to somewhere, in this case, this value of memory, and the value of IP is may or may not crash the program, but it crashed the program at the end. Try to run that by yourself and try to run this operation. So you put the breakpoint, you run step by step by GDB or by DDD, it's the same, and reach the point where the value of IP is something strange. How to play with that? This is the value of the pointer. Depends on the contents of the memory at this time, at the moment. Everybody should have a different one. So we need to initialize the variable at the beginning. You see that sometimes crash and failure of program are not so easy to discover the main reason of this behavior. A third example, to make a big memory allocation, and of course we get an invalid memory address there. Try to print the value of this and you will see why. So you run, you can backtrace it. Backtrace is often, it's go back from where it crashed to where it were called. So the subroutine which called the portion of code, you get back to there with the stack push up, and the value of the code can be print and discover where it crashed. So let's go with this example fund. segfault. G minus O fault dot x. That's it. Run it. The correct version, or maybe I fixed that. Oh yeah, I've changed the value. If I let the value has indicated in my slide, it's too big. Okay. I want just GDB. It's also feasible if you want to try. List in the list. Break. We put a break line, for instance. Just the. I don't know if comments can be break. I think that there is a break there. List. Run. Did I compile? Malloc is not, of course. Next. There, the program crash. Backtrace. Trace. I don't know the short. No stack. Oh, I've left the segmentation violation when I run print buff null pointer. So the size of this is the main reason where the memory allocation failed, and segfault, of course. Common use and easy to discover this kind of error. This last exercises, I can let you play with that. It's funny because you get a character from the keyboard, from the standard input, and then it tried it and it never stopped. Or how to find a solution in this case. You can control C by breaking it, interrupting it, because it will fill the screen of the letter you have typed. So debugger is, yeah. I know it's more difficult today to speak and to present because usually this training session was more interactive with user in the computer room and we work together. So I'm presenting it. I don't know how how many time to wait before I present a way to use GDB. So do that by yourself at home, relax, and play with DDD, GDB, GDB-IA. If you have a parallel program, try with debug parallel. You can come to me when you have specific question with your own code, with your own question, and we can search together how to use at a real scale a debugger. Another way to search problem in the, and I just mention it so you can also try to use it, is Valgrind. Valgrind is a tool, a GNU tool, an open source software, piece of software, often used to search for memory leak of problem of memory. When you open an array in the subroutine, you have to disalocate it at the end of the subroutine when you leave it if inside the scope of the subroutine. Otherwise, every step you enter into this subroutine, you allocate a portion of memory. And it was often the case with in the past with Firefox or Netscape. Netscape, if you run that after some days, it takes gigabyte of memory and you have to close it, otherwise the machine begins to swap. It's due to not so well written code when you forget to unallocate or free a portion of memory which are not needed anymore. And with Valgrind you can search or plenty of other stuff, the inappropriate type of variable put in the argument of a subroutine or things like this, that can be discovered by Valgrind. For important code, it's a common way to search for this kind of problem. And this example can be played with Valgrind. Memory memchecker, there are plenty of extension with Valgrind, memcheck, leak check, and so on. Also on the valgrind.org website, there are tutorials, there are examples, and it exists also a graphical tool to use Valgrind. And if you needed that, play with Valgrind and return to me or to the team or to other member of CISM or CC team, and we can search together if you have a problem of this kind. I think that for the debugger, I've made a full round of the different aspects of it. This afternoon, I'm going to talk about profiler with amplifier and also trace generator and help to tool to help to improve your code, to search where to put parallelism, where to put emphasis on certain portion of subroutine which are more often called or take more time, which are the loop that should be parallelized. Is that the inner loop? Is that the outside loop? So I see you in 2 hours. I think I don't know by heart, but
I think it starts back at 2. Let me check.
is that?
Yeah, confirm it. It restarts at 2.
Okay. It's
So,
the continuation, if you want, of this this one tour of Intel Cluster Studio software.
yeah.
Thank you for your attention, and enjoy your meal.